All right, so hello and welcome back to our stream here at OneClass. Again, my name is Joey. I'm going to be your chemistry teacher for this session. Today is Thursday, so I'm going to be streaming some chemistry problems for you folks at home. If you're tuning in for the first time here at OneClass, well, a little bit about ourselves. So what we're doing here is we're creating some live streams and videos for you for basically frequently asked questions. And these questions are submitted by folks like you at home, students like you at home. And what we're doing here is as OneClass teachers, we are verifying these solutions to provide you the best kind of results as you move forward in terms of your tests and assessments. So throughout these questions, we'll be teaching you the concepts behind the question, and then so that you'll be kind of better prepared for when classes do start again, when you're back in school, like physically. So here at OneClass, what we're doing is we're providing these free online resources for you to access basically anytime at youtube.com/OneClass, and you can find out all these videos are already recorded as well, and you can join us in the, on the live stream as well if you want to tune in live. So just a little bit about myself. Again, my name is Joey. I'm currently a secondary school educator in Ontario, and what I'm doing is my teachable subjects are chemistry and also and music as well. But I'm planning to get my math teachable further down the road as well. So without further ado, let's get started on kind of today's lesson. And what we're going to do today is probably focus on, I have like one grade 12 chemistry question in terms of the senior level, but most of my questions here are going to be in the grade 11 curriculum or the first half of general chemistry. So let's get started here. All right, so what we have here is it says determine whether HI, so a hydroiodic acid, can dissolve each metal sample. If it can, write a balanced chemical equation and showing how the metal dissolves in HI and determine the minimum volume of 3.5 molars of HI required to completely dissolve the sample. So we're given basically, we're given hydroiodic acid. So let me write this down here. So in this number one, we have 3.5 molars of HI, and this should be an aqueous solution. So we know it's hydroiodic acid, and we are given basically three metals. So A here is aluminum. So we have 2.5 grams of aluminum. B here is we have copper, Cu, and then this would be 4.85 grams. And finally, C, we have, this is silver, and we have 2.42 grams here. So it says here, determine whether or not HI can dissolve any of these metals here, right? So when we talk about this concept of dissolving metals, of reacting with metals, we have to talk about this concept of the reactive series, right? And unfortunately, because we have it's not a displacement activity series like you see in a single displacement reaction, because we don't have a metal displacing another metal, right? And the iodine here is, the iodine in hydroiodic acid here is a non-metal. So what we have to do is we have to actually look at our standard reduction potentials, and I kind of brought it up here as well. So you can kind of look at the half reactions in terms of the standard reduction potentials, and look at your potential as well, and see whether or not this reaction will take place. So let me write down these values for you. So I have HI here, which means I have to go in terms of my half reaction here, and I'm finding iodine. So I know here iodine 2 here, I2 plus 2 electrons here. When it becomes oxidized, I would get 2 iodine with the negative charge here. So this is the iodine anion here. So this is a reduction, not oxidation, right? Because I'm gaining electrons here. So these are all standard reduction potentials every time I gain an electron here. And this says the iodine here is positive 0.5355. If you want, you can also write out the reaction here. If you were curious here, again, HI dissolves into basically H2 plus I2, and this here obviously have to balance chemical equation here, and then obviously I2 here would then be reduced, right? So I would gain 2 electrons here, and it would become I minus here. So this here would be the reaction that would happen here. So again, I have a 2 here as well, and this here again positive 0.5355, right? So positive 0.5355. So basically what I'm doing now is I have the standard reduction potential, and I'm looking at all the other standard reduction potentials for aluminum, copper, and silver. And if it lies basically below this below the standard reduction potential, then then I'll be able to dissolve the metal, right? So let's look at aluminum here. Aluminum first lies on, let's see, Al lies over here, right? It's a negative value here, negative 1.662. So knowing that here, I'm going to write here negative 1.662. And this is simply just the reduction potential of aluminum here. I'm going to try to find copper. Copper here is, depending on what charge it is, it would probably be a different kind of yeah, copper here would be I think they just had the 2+ here, so the copper here is 2+. This would be positive 0.337. So this is positive 0.337. And then finally for silver, I would have silver here would be over here, right? This is 0.7996. So this is positive 0.7796, right? Yeah, 7996, sorry. 0.7996, and basically we're looking at these standard reduction potentials here, and we're looking at which one is furthest apart from positive 0.533 in terms of difference, the difference here. And we're going to realize that the difference here is aluminum here, right? The difference between 0.5335 and what negative 1.662 has the greatest difference here, which means it's going to dissolve the metal. So aluminum here is our correct answer. So I know it's going to be A. So I know it's aluminum, and it says here I have to write out the balanced chemical equation. So let me just do that real quick. So if I know it's aluminum, then I have a, so I'm going to have hydroiodic acid. Hydroiodic acid plus, this is aluminum, right? Plus aluminum here. It's going to react and form, let's see, aluminum. You would probably get aluminum hydride and aluminum hydride, and there's the I minus, sorry, the iodine anion here. So this would react to probably form, would be aluminum hydride, AlH3, and you would get the iodine negative here. So you get probably, if I want to balance this out, you would get something like this. So 3 iodines here and 3 iodines here. And then, again, this would be, again, oxidation reaction, so redox reaction here. And we're given here we're given 3.5 molarity of HI, right? And I want to dissolve 2.15 grams. So what I have to do is, again, I have 2.15 grams here. This is in moles. I would have to basically figure out, mass, sorry. So I have to basically figure out the moles of this solution here, right? So again, I can figure out my molar mass if I were to look at my periodic table. So if I look at my periodic table here, aluminum has a molar mass of 26.982. So this would be molar mass here. This is 26.982 grams. And then I can figure out my moles, right? My moles is simply just my mass divided by my molar mass. This is 2.15 divided by 26.982. This would give me a value of 0.07968. 0.07968. So this is in moles. And basically what I want to do is I want again, by balanced chemical equation, I'm going to have 3 I'm going to have 3 the coefficient here is 3, right? So I have to figure out a mole to mole ratio for this HI here, which means I would have to multiply this mole ratio by 3 in order for us to get the moles of HI here. So if I were to do that and multiply this number by 3, I would get, this would be 0.2323905. Remember, this here is separate. So this is the moles of HI here. If I have the moles of HI, what I can do is I can now solve for my volume, right? I know my concentration equals my moles over volume. So concentration here is 3.5 molars. I'm going to have my moles here, which is 0.23905. And I'll have to solve for my volume here. So I simply have to just, I'm going to have 3.5 V times V equals 0.23905. And finally, volume would just be 0.23905 divided by 3.5, which would give me a volume of 0.068 liters. I could convert that to milliliters by multiplying by 100, which means I only need 6.83 milliliters for me to dissolve my acid, dissolve aluminum in my acid here. So this here is the correct answer, 6.83 milliliters here. And I don't think that this is an incomplete solution here, because they didn't really show me the balanced chemical equation or the actual answer. So I believe their logic is right here, where it says they're finding the molar mass and they're calculating the moles, but I don't think they actually gave me the answer. So I'm gonna write here solution is incomplete. Aluminum would be the one that would be aluminum would be the metal that is dissolved. The volume that is needed would be 6.83 ml to dissolve. This would dissolve what's the mass here? Mass was 2.15 to dissolve 2.15 grams of Al here. So again, I think their logic here was right when they were trying to find out what kind of like logic when we're approaching the answer. But I believe that they had the question they had the question wrong here. So that's so they simply just missed out on the concept here. I think I'm looking at my balanced chemical equation. I don't think I actually get aluminum hydride here. I think I get I'm pretty sure I get aluminum iodide and H plus actually, and hydrogen gas here. So this is actually an incorrect thing here. I'm just looking back. I'm like, oh, this is aluminum. Here's the 3+ charge is going to go with the negative charge, obviously here. So this is my fault. This should be Ali3 plus H2 gas. So this is actually going to change my coefficients here. So that's not good. So I'm going to have here, this would be a 2, this would be a 2, this would be a 3 here, right? And then I would have to have a 6. Yeah, so 6223 would be my balanced chemical equation, which means actually my moles of this will change. Let me just check here. 6 iodines. Yeah, so actually my moles are going to change here, because I'm going to have to basically divide this moles by 2 to figure out the aluminum, and I'm going to multiply by 6. So just give me a second here. 0.07968 divided by 2 times 6 here would give me 0.23905. Oh, so this is actually the same thing. 23904, which is actually so my volume here is correct, just because I got lucky, and the multimole ratio was still 1:3. However, I wrote my balanced chemical equation wrong here. So let me just correct this here. But the volume is correct. And then I'll write here, the balanced chemical equation is 6Hi plus, this would be 2Al, yields 2Ali3 plus 3H2. So this here would be my balanced chemical equation. So solution here is, I'm going to write here incorrect because it's an incomplete solution here. All right, so that's number 1. This here is number 2. So asking, how do I calculate the pH of NaOH? So this is kind of a very vague question. So if I were to calculate the pH of anything, I need to be given concentration. Calculate pH of NaOH. So how we calculate pH, usually we have this formula here. pH equals negative log of our hydronium ions, H3O plus, right? However, if you have NaOH, if you think about this NaOH as it's a base, right? So it's actually not going to give you H3O plus. It's going to give you actually hydronium ion, hydroxide ion, sorry. So you can actually use this relationship between POH, which is negative log of our hydroxide ions here, H3O, OH minus, sorry, OH minus here. And then we can know that pH plus POH has to equal 14. So basically, in order for me to calculate the pH of NaOH, what I would have to do is I would have to be, again, given some concentration of the NaOH here, and then I know that NaOH here is a strong base. It's going to dissociate fully in water. So this is a strong base. So if I were to write the balanced chemical reaction, I would have NaOH plus H2O. This would go only in one direction here, and it would give me, I would get OH minus here. I would basically get Na plus and OH minus here. It's going to dissociate into a base here. So I would get, you can think of it as Na plus plus OH minus here, and then and you get water and whatnot here. So you could think of it as you could think of it as, or actually you can think of it as Na plus would be just like a participant ion, and it's just gonna fully dissociate, right? So you can think of it as this, as NaOH yields Na plus plus OH minus here, and this OH minus is going to affect our pH here. So if you have the concentration of OH minus, you can simply plug into this pOH formula and then solve for it using pH plus pOH equals 14 here. So again, this here is correct. Again, they use the exact same expression here. They know that they ionized here like so, and you can simply find out the concentration using this formula here. So the solution is correct. Again, I wasn't given a concentration in the question, so I can't actually solve for it, but the logic here is correct here. Whereas there's relating pH with pOH, and then they're writing down the ionization reaction for NaOH to solve for my concentration of OH minus here. So the solution here is correct. It's correct. Good analysis here. Okay, this is number 2. Number 3 is asking, write a formula for the ionic compounds that form between each pair of elements here. Okay, so this is a pretty easy question. We know that they're given ionic compounds, so I know it's going to be a metal and a non-metal, right, for ionic compounds. So this will probably be asked in actually a grade 10 class here. So ionic compounds, again, I would get, so A here says I know it's calcium and oxygen here. I would get B would be zinc and sulfur. C is rubidium and bromine. And finally, D here would be aluminum and oxygen here. So basically, when we look at these problems here, there's 2 methods you can use. You can basically use the crisscross method, or you could use kind of logic in terms of how do you balance out the charges here. So I'll show you both of them. I'll show you, I guess the first 2, I'll show you the crisscross method, and then I'll show you the balance the charge method here. Personally, I like balancing the charges myself, just because crisscross method is kind of repetitive in terms of like, it's kind of the quick and dirty way to kind of like figure out the answer here, but it doesn't really actually teach you the concept of what's actually happening in terms of the atoms here. So let me look at the first one here. We have calcium and oxygen. So what we're going to do is we're going to break this down to charges here. So calcium, I'm going to look at my periodic table. As you can see, calcium lies on the second column, right? It's an alkaline earth metal. So calcium would have a charge of 2+. So Ca would have a charge of 2+. Oxygen, it's a non-metal, right? So we will look here on my right side. As you can see, oxygen here lies on group 16, which is the O here. If it's group 16, which means I will have a charge of 2-, right? I have 6 valence electrons, which means I need 2-. I need 2 more electrons to fill the octet here. So 2- here. So in order for me to solve for the ionic compound here, you could use a crisscross method. So basically Ca2, the 2+ here charge will become the coefficient for O2- here, and the 2 here would also become the coefficient for the Ca here. So you get Ca2O2, and you can simplify this even further to just simply CaO, right? Because these 2 can reduce to 1 here, and you get CaO, or calcium oxide here. So that's the correct solution for my first answer here. I can do the exact same thing for zinc and sulfur, right? So if I look at the periodic table, zinc is actually zinc here is kind of a special metal where it's multivalent, right? So when we talk about zinc as being a multivalent compound here, it's going to have basically more than one charge. In this case, we don't really have a charge here. So I'm going to assume that it's 2+, which is the most common charge for zinc here. And let me try to find zinc for you. Zinc is here. Zinc, because group 12 again have a charge of 2+ here. So I'm going to assume zinc here has a charge of 2+. And then sulfur here, if I look at my periodic table, sulfur here lies over here, right? This group 16 again, I have it's under group 16. Sulfur here will have a charge of 2-, right? 2- here. I can then employ the crisscross method. So my coefficients become, the charges become the coefficients of the opposite element, which means I'm going to get Zn2S2, which I can simplify further to Zns, right? So zinc sulfide here will be my correct answer, or zinc 2 sulfide would become my answer for this problem here. So that's the crisscross method. I'll show you the one I use, and this is the one that I kind of like balancing out the charges here. So I have rubidium and bromine here. So let me go back to my periodic table. Rubidium relies on the first column here in the metal section, and as you can see, rubidium here relies on group 1, which means rubidium would have a charge of 1+. So let me write down rubidium here. So Rb would have a charge of 1+. Same with bromine here. Bromine is a nonmetal. It's going to lie on group 17 here. It's a halogen, and it's going to possess a charge of 1-, right? So Br would have a charge of 1-. And what I'm going to do is, instead of crisscrossing, what I'm going to do is I'm going to think about this logically. I'm going to think about how do I balance out my charges to get a net charge of 0. If I want to get a net charge of 0, I have 1+ here and 1- here, right? So 1 + 1 + -1 will give me a charge of 0, which means I don't need to add any coefficients here in order to make my charge 0. So in this case, I can just simply write Rb Br would be my answer here. It's just simply I only need one of each atom for me to balance out the charges here. So that's going to be my correct answer for C. And finally, aluminum and oxygen, right? So I'm going to look back at my periodic table for aluminum. And aluminum lies under here, right? Under group 13 here. So this here is Al. Well, it's going to have a charge of 3+ here. So aluminum, so I'm just write Al here, has a charge of 3+. And we know the oxygen from before here, oxygen here has a charge of 2-, right? So I'm simply just going to write 2- here. 2-. And again, I want a net charge of 0, right? If I want a net charge of 0 here, I have 3 positives and I have 2 minuses here, right? If I add the two numbers up, I'm going to get a net charge of +1, which is no good. I want a charge of 0, right? So in order for us to do that, how I think about this problem here is I can think about using lowest common denominator. So in order for me to get the lowest common denominator between 3 and 2 here, this would be 6, right? I would get a lowest LCD here of or I guess it would be greatest common factor would be 6 here, right? So if I wanted to get that, I would basically have to add a 2 in front of aluminum and a 3 in front of oxygen, right? This makes it so that's 2 times 3+ here, which means aluminum would have a charge of 6+, and 3 times 2- here, which will give me a 6- here. 6+ -6 will give me a net charge of 0. So therefore, I'm gonna only need aluminum has to have 2. I have to have 2 aluminums here, and then oxygen will have 3 here, right? So this is Al2O3, which is aluminum oxide. So these are my correct answers here. So I'm going to have, again, CaO, Zns, RbBr, and Al2O3. So this will be my correct answer for this problem here. This is a very, very long solution, and I don't think they actually added my I don't think they actually wrote the chemical equations. This is actually, again, another incomplete solution. I'm just gonna write it down here. So AB was calcium, oxygen, and calcium and oxygen make calcium oxide. So CaO. B is zinc and sulfur make zinc sulfide. This is Zns. C here is rubidium and bromine make rubidium bromide, which is RbBr. And finally, D here is aluminum and oxygen make aluminum oxide, which is Al2O3 here. So this here is my incomplete solution. There's great logic behind it, but they forgot the chemical formulas for the ionic compounds. So I'm just going to say a solution is incorrect just so they can add this into the system here. Okay, that's number 3. So number 4 is asking how many grams of chromium-2 are present in 1.16 grams of chromium-2 nitrate. And number 2 says how many grams of chromium nitrate can be made from 4.49 grams of chromium-2. Okay. So number 4 is asking, so I have chromium-2 nitrate, and I have 1.16 grams of chromium nitrate. So let me write this down. 1.16 grams of chromium nitrate. So chromium here, I'm going to look at my periodic table. Chromium here belongs in group 6 here. So Cr here. And it says Cr2. So I'm going to know that this charge is actually a 2+. So Cr have a 2+ charge. And nitrite is one of our special polyatomics, right? So if I recall, nitrate has a charge of NO3 minus. Nitrite will have a chemical formula of NO2 minus here. So this is NO2 minus here, which means my formula for chromium nitrite would be CrNO2 and 2 here. So this here will be my chemical formula for chromium nitrate. And again, I have 1.16 grams of this. So it's asking us how many grams of chromium-2 are present in 1.16 grams of chromium nitrate. So what I'm going to have to do is I'm going to have to find the moles of this compound here. So I have 1.16 grams here. So so that's my mass here. So mass here is 1.16. I'm going to have to find the molar mass of CrNO2, right? So the molar mass would simply be chromium, which is 51.996 is my molar mass of chromium. So I'm going to write that down. So it'd be 51.996 plus how many nitrogens I have. In this case, I have 2 nitrogens, right? This N here has a subscript of 2 here. I have 2 nitrogens, so I have 2 times 14. I would assume here is 14. So 2 times 14 here is 28 plus 28. And then here, oxygen is O2, and I have another 2, which means I'm going to have O4 here. So O4, again, my oxygen here has a molar mass of 16. So 16 times 4 would give me 64 grams per mole, right? 64 grams per mole. I'm going to sum all this up to give me my total molar mass for chromium nitrate. I'm going to get 51.996 plus 28 plus 64 will give me 140.996 grams per mole. So 140.996 grams per mole. And then also, so I'm going to have, so this is my molar mass here, and I'll find moles specifically, right? Moles of the entire compound here would give me, so I get 1.16 here. I'm going to divide it by the molar mass, which is 140.996 here, which would give me a value of this 8.227 times 10 to the negative 3 moles here. So this will be my moles of chromium nitrate. And what I'm going to do is with this mole value here, I can figure out, okay, what this is my total amount of moles here. So how would I have to break it down in terms of atoms here? So I'm going to have to break this element down to atoms and see how it creates this how it fills up this moles here. So think about CrNO2, right? CrNO2 and 2, right? So if you break this up into your atoms here, you can visualize this as you have 1 chromium. Let me use a circle 2 here. So you have 1 chromium atom, and you also have 2 nitrites, right? You have 2 nitrites here. So you also have you have NO2, NO2, and you have NO2. So this is how so these are the components of your CrNO2, right? So you have chromium and you have 2 nitrite polyatomic ions, right? So in order for this to have moles here, what it's comprised of, again, it's comprised of 3 parts, and they all play an equal part in creating this mole value here. So basically, if I have 3 parts here, I'm going to divide this mole value by 3 in order for me to get how many moles of chromium are there specifically, because I only care about the chromium ions here. So if I divide this number by 3, so I'm going to divide the number total by 3 here to get me basically the moles of specifically only chromium here, which is 2.74 2 times 10 to the negative 3 moles. And what I could do with this is I can convert this back into my mass here. So if I want to convert back to mass, again, I would have to simply just use again, mass equals moles. Oh, sorry, moles equals mass over molar mass. So I have to multiply this by our molar mass of our chromium. So this is 51.996 grams per mole to give me the grams of chromium here. So I'm going to take 2.742 times 10 to the negative 3 here, times 51.996, which would give me the grams of my chromium here, which is 0.143 grams of chromium. So this here is my grams of chromium in chromium nitrate. So let's see here. So let me just see if they got the answer here. Moles is 1.16 divided by, so this here is correct, and the moles of here, chromium in samples times 52, 0.082 times 0.41 times 52 give me 0.416. So they're just simply actually doing, so they have the moles here, and they're actually just converting it back into molar mass here. So they're not even, so they're actually not even dividing by 3 here, and they're simply just moving towards they're simply just multiplying by the mass to get the moles here. So actually, I don't think you have to divide by 3 here. So I think I actually got the, sorry about this. So again, I think I divided by 3 because I thought we were doing a multiple ratio, and instead we're not reacting with anything. So this is actually my fault here. I thought we were reacting it with something, where in reality we were just calculating the moles here. So this here, I don't need to divide by 3 here, and I can actually just simply convert it back into mass here by multiplying this by this number by 51.6, so 8.227 times 10 to the negative 3. I can simply just multiply it by 51.996 to give me the mass of my chromium here. So sorry about that. So it's 8.227 times 10 to the negative 3 times 51.996. So this would give me 0.427, and they got 0.4, kind of close here, but 0.416. Series grams, and then I can multiply 0.227 times 10 to the negative 3. I can multiply that by whatever 28 plus 64 is to get the mass of my nitrate here. So it's 92, which would be basically 1.16 minus 0.427. to get me the remainder of my moles here. So this is 0.733. Yeah, 0.733 grams of NO2. This is CR here. So this here would be like the mass composition of chromium nitrate. And then finally, B is asking me how many grams of chromium nitrate can be made from 4.49 grams of chromium 2. So what you could do with this one is you could either take a percentage to figure out this problem here, or you could just use, again, mass to moles, right? So if I were to do B as well, it says how many grams of chromium nitrate can be made from chromium 2. So if I have Cr2, I have 4.49 grams here. And again, and I can convert this to moles by dividing by the molar mass, right? I know my molar mass here is 51.996 grams per mole. So which means my moles here would be 4.49 divided by 51.996, which would give me a value of 0.0864 moles here, right? So this here is my moles of chromium. And what I could do is I could go back to my chromium nitrate here. So again, chromium nitrate, my chemical formula for that would be 0 CrNO22, right? So if I have 0.864 moles of chromium here, I can also figure out, again, how many moles I have of this nitrite group here as well. So again, what they did here, they again calculated the amount of moles like so. So to make 4.49 grams of chromium nitride here, the amount of chromium 2 requires 4.49. We're dividing it by the total molar mass, which is 144, or as I calculated, 140.996, and we're multiplying it by 52 here, because that's the molar mass of chromium here. So again, you could do with 4.49 grams is again divided by, you can take 4.49 here and divide by 140.996 grams per mole. This would give you some value. Let me do this one. 4.49 divided by 140.996. So you get 0.0318 moles here, and you can multiply this by 51.996 to only get the mass of my chromium, or the mass required of CR2 required here. So this is 1.621 grams. So just like how they, or 1.655, sorry, 1.6556 actually grams of chromium here. So that means you can get how many grams of chromium 2 nitrate can be made from 4.49 grams of chromium 2. You can make 1.656 here. So solution here is correct. The numbers are slightly off, but the logic is there. So solution is correct. Great analysis here. I got specifically slightly off numbers just because I have the molar mass was slightly different, so it's totally fine. That's number 4. Okay, look at number 5. It says, which of the following isotopes would you expect to be stable? Okay, so you have this is 234 Pa, you have 4 helium, carbon 12, 238 uranium here, and 58 nickel here. So it says, which of the following isotopes would you expect to be stable here? So if you look at the first one, Pa has an atomic mass of 234, right? So you would expect Pa to be somewhere here. It's protactinium. This here it belongs in our actinide groups here. So this here is actually a very unstable group. Proctactinium. I can't pronounce that. Whatever. Pa here is, again, it's right beside uranium here, which is actually very, very reactive. So these isotopes, these elements here are going to go through radioactive decay or alpha decay or some type of decay to basically release energy here. So this one is definitely not stable. Pa is not stable here, and you can assume that uranium is also not stable because, again, these are very, very highly radioactive isotopes here. So you're left here with helium. Helium, carbon 12 are pretty stable as isotopes, just because they exist kind of in the further up on the periodic table. And nickel here as 58 would also be stable here because, again, it's not a radioactive isotope here. So these 3 compounds would be more stable here. So again, most stable compounds are helium, carbon, and nickel here. That's good. And then Pa and uranium have a greater atomic number than 83. So 83, you can say it's the cutoff for depending on what do you think in terms of radioactive decay here. So you can say that basically like normally elements that are further down the periodic table are less stable than the ones that are at the top. So the solution here is correct. Good analysis here. Okay, that's number 5. Number 6 is asking, what is the molar mass of calcium chloride? It's a very, very easy question here. It says molar mass of CaCl2. So if we want to calculate the molar mass of CaCl2, we want to break CaCl2 back into its original compound. So we have Ca and we have Cl, or we have 2 Cls, right? We have 2 Cls here. So Ca, if you look at your periodic table here, it belongs in the second group. So you have this here is 40.078, right? So you have one Ca molecule, so it's 40.078 0.078. Sorry, one calcium atom, not molecule. And chlorines, I have two chlorines here, and each chlorine possesses a molar mass here of 35.45 here, right? Chlorine belongs in the group 17 here. It's 35.45. So if I multiply that, I would get 40.078 plus whatever 2 times 35.45 is. So 2 times 35.45 will give me a value of 70.9 here. 70.9. I add both of these numbers up to give me my total molar mass of calcium chloride. So this is 40.078 plus 70.9. This will give me a value of 110.978 grams per mole here. So this is my solution for this problem here. And again, they had 110.98 here. So the solution here is correct. And again, what they did was they broke this down into the molar masses like so 40.08 and 35.45, and then you realize there's 2 chlorines here, so you have to multiply that number by 2 here. So the solution here is correct. Solution is correct. Good analysis. Oh. Interesting. Okay, I have an organic chemistry question here. I think I accidentally plugged this in by accident. Sorry. So this is not in grade 11. Don't worry about this. But nonetheless, I guess I'll verify this question for you as well. So asking, draw the most stable form of the major mixed Claisen product form in the following reaction here. So this is probably the university level chemistry. So sorry if you sorry about the folks at home that were tuning in. I did not know that I put this question in, but it's okay. We'll roll with it for this one here. So again, I have so in this case I have two ester groups, right? And basically it's a Claisen product formed by this reaction here. So the first step here is I don't know if I have space, but this is sodium. This is NaOC2H5 here. The second part would be an acid workup of base material plus, and it's done under I'm done under ethanol as my solvent here. So this is a Claisen product here. So when you look at the Claisen, you can think of Claisen as a condensation reaction here, right? So you can think of, again, I have 2 ester groups. Again, I have the carboxylic acid group. Like so, and I also have I have basically 2 esters here. So how this is going to work out is that it's going to basically condense and form some type of like keto ester. So it forms an alcohol firstly, and then it forms it's going to form my kind of like an anhydride group. So I'm going to draw out the compound here, and yeah, let me just draw the compound here. So you would get something like this. You would get basically your first compound looked something like this with the bond O here, and you would get basically this would be the other double bond for this guy here. Let's see. So you get one here, and you would get bond O. Bond plus, and then you get ethanol here. So this here would be my the most stable form of the mixed Claisen product here. You basically form an anhydride by placing 2 esters here. You can think of this. You can think of the mechanism as if you had the lone pairs of one of the one of the alcohols are going to attack basically the double bond here, because I know that this here is partial positive, this here is partial positive, and then this here would be partial negative here. So again, you have there's a dipole here, and what it's going to do again, one of the negative oxygen groups from basically the sodium here, the sodium. Well, the O here is going to attack one of these guys here, and then you form an alkene here with the O minus here, and then what it's going to do is it's going to collapse on itself and then attack also the other carbonyl group, and you basically do an acid workup to neutralize that the O minus here to form the two double bond O's here. So this here would be my answer for this problem here, and this solution here is correct. I believe I have 1, 2, 3. Let's go to 4. I think they're missing a carbon here with this problem. Let me just check. Oh yeah, no, the carbon's here. So 1, then 2. Oh no, it's not. I think they're missing a carbon here. Let me just count carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I have 11, so it's my fault. So this here is the correct answer. So this here is the correct answer, and good solution here. So I miscounted my carbon, sorry. So the correct solution, and no analysis provided. But it was just simply a fill in the blank question here, right? It's simply a condensation reaction with acid workup to form an anhydride group. Or you can think of it as a beta ketoester. The solution here is correct. Sorry for adding this question. I thought that I was going to do Orgo probably next week, because I already did Orgo this week as well, because I was going to focus on some grade 11 problems, but it's okay, we got that out of the way, so don't worry about that. Let's look at number 8. That was number 7, right? Yeah. Number 8 here says, what solutions of silver nitrate and calcium chloride are mixed, or when solutions of silver nitrate and calcium chloride are mixed? Silver chloride precipitates out of the solution according to the formula. What mass of silver chloride can be produced from 1.26 liters of a 0.160 molars of solution of silver nitrate? So let me just write this down. I have 2 AgNO3 plus CaCl2 would give me 2 AgCl plus CaNO3 2 here. It says what mass of silver chloride can be produced from 1.26 liters of a 1.60 molarity solution of silver nitrate. So silver nitrate was this guy here. So I have, again, this case I have my molarity, or my concentration, I'm going to say. This is concentration, which is 0.160 molars. And I have my volume, which is 1.26 liters, which means I can solve for my moles instantly, right? Moles is simply just C times V here, right? Because the concentration is moles divided by volume, which means moles is 0.160 times 1.26 here. So it's multiplication, right? So give me 0.2016 moles of solution here. And again, as you can see, I have my coefficient here is 2 for silver nitrate and 2 for silver chloride here, right? Which means my multimole ratios here are exactly the same. So again, silver chloride, which means we'll also have 0.2016 moles. And then simply I would have to basically find the molar mass of silver chloride and then to find the mass of silver chloride. So I'm kind of going, I'm kind of just using stoichiometry to figure out this problem here. So I need molar mass and finally my mass here, right? So silver chloride, again, silver, I have Ag here, which is 107.87. So I have 107.87 plus chloride, we know it's 34.45, which will give me a total molar mass of 107.87 plus 35.45. We give me a total molar mass of 143.32 grams per mole, and we can simply just multiply both of these guys to figure out the mass, right? So 143.32 times 0.2016, which would be a mass of 28.89 solution grams, 28.89 grams of solution here. So that's number A. So A here is correct, right? They wrote 28.88. I wrote 89. Same thing. This here is my solution for A, which is awesome. And B here says the reaction described in part A required 3.49 liters of calcium chloride. What was the concentration of this calcium chloride solution? So they're now looking at calcium chloride here. So let me do this in blue. And they required 0.49 liters here. So basically what I'm going to have to do is, again, if I want to figure out the mole, I want to figure out the concentration, right? And I'm going to have to figure out the moles first. Someone says hi. I says hello. I say hello as well. So I'm going to have to figure out my moles first, right? So if I have 0.2016 and this has a coefficient of 2 here, I'm going to have to divide it by 2 to get the calcium chloride moles as well. So 0.206, I'm going to have to divide that by 2. 2016 divided by 2 to get me basically the moles of calcium chloride here. So 0.1008 here. So that's being the moles of calcium chloride, and then I'm gonna have to multiply that by I'm gonna have to divide my moles by my volume to figure out my concentration here. So this guy has a question. Yeah, you can shoot. Just type on the chat, and if I have time today, I'll try to answer the question here. So I have C equals N over V, right? So concentration equals moles over volume. So I'm going to have 0.1008 divided by 3.49 to get my concentration of my calcium chloride, which is 0.0289 here. 0.0289 molarity here. And this here is going to be my solution. Again, this here is the correct solution for this answer as well. So the solution here is correct. Solution is correct. Good analysis provided as well. So that's number 8. Number 9 is asking again a molar mass question of sulfuric acid. So again, very, very easy. Molar mass questions are very, very easy to solve because you simply just have to look at the periodic table here. So number 9 is again molar mass of H2SO4. So you want to break again H2SO4 down to its atoms, right? So we have H, obviously, we have S, and then we have O. And then how many H's do we have? We have 2 H's, so it's going to be 2 times basically the molar mass of hydrogen, which is 1.008. So 1.008 grams per mole, and that would equal something. I'll calculate after. Sulfur, again, I have 1 sulfur atom times basically the molar mass of sulfur here, which is 32.06 here. I don't know that chemist, I'm sorry. 32.06 grams per mole. And then finally, oxygen, I have 4 oxygens in here in SO4, right? So 4 here times, it's going to be 16 grams per mole to figure out something here. So I basically have to plug this into my calculator, right? I have 2 times 1.008, which will give me 2.016. 2.016 grams per mole. 1 times 32.06 would be obviously just 32.06, and 4 times 16 here would give me a value of 64 grams per mole. I simply have to add all of these up to figure out my total molar mass rate. So I have 2.016 plus 32.06 plus 64 would give me a value of 98.076 grams per mole, and this would be my molar mass of my sulfuric acid here. No, sorry, I don't know German. Yeah, no, can't speak it, sorry. This here, my answer for this question here is 98.076, and I'm going to scroll all the way down. This here is correct. So they basically did the same thing again. They found the molar masses of hydrogen, sulfur, and sulfur and oxygen, and they basically just broke this down into their atoms here. So the solution here is correct. Solution is correct. Good analysis here. And then let me see if I can squeeze one more question here. I might be able to do it. So let me do number 10 and finish off 10 problems for today. So asking, what is the molarity of Cl minus in each solution? So part A is 0.188 molars of NaCl, and part B would have 0.200 molars of SrCl2. So part A, I have some type of I have concentration, right? Here's, so NaCl is the concentration here. So NaCl is going to dissociate into its ions, right? So NaCl will dissociate into basically Na plus plus Cl minus. If I have the concentration of 0.188 molarity here, I'm also going to have 0.188 molarity here. So the concentration of sodium chloride here, of chlorine ion, is 0.18 for part A. And then finally for part B, let me do some blue. I have the strontium chloride. It's going to dissociate to, I have Sr, I believe it's, Sr here is 2 plus Cl minus. I'm going to have to balance this chemical equation first. There's going to be a 2 here. So in order for me to do that, again, I have 0.200 molars here, which is, so my concentration of chlorine is going to have to be 2 times 0.200, which is 0.440 to get my concentration of the chlorine ion here. So the solution is correct, 0.188 and 0.400 molars. So the solution is correct. Good analysis here. So the solution here is correct, and I believe that's probably going to be the last question of the day. I might be able to actually do this. Hold up. I have 3 more minutes left. Maybe I'll do this. I'll finish off at 11 as well, just to figure this out. So it's telling us to write the Lewis dot structure for C2H6. So I want the Lewis dot structure here. So for me to figure this out, I have carbon and carbon here, right? So you can assume that the carbons are going to be bonded together here, just because carbon here, we know that it can make 4 bonds. So carbon here and carbon here, which means carbon is going to, I kind of got rid of our carbons because I know it's carbon bonded carbon, and I have 6 hydrogens here, right? So I'm going to have to, I basically just have to saturate these carbons, right? I have 1, 2, 3, 4, 5, and 6 here, right? So I can just simply fill my hydrogens here. And this here will be my answer for this Lewis dot structure. This is actually the structure of ethane. And what it is again, you can think of this as, this is the skeletal structure here. Again, you can think of it as counting valence electrons. Carbon here can make 4 bonds. Carbon here is making 4 bonds, which is awesome. That's basically about it for this structure here. So so this here is the bond, the structural diagram for this, but you can also draw the Lewis dot diagram by simply just replacing these by with electrons, right? So again, this diagram here is correct when you are when they have because they're sharing kind of electrons like so. So this here is again a correct solution here. Again, what I'm doing is, again, carbon's making 4 bonds. It's full in terms of the octet here. This one is also full in terms of octet. Hydrogen's happy because it has 2 electrons. So the solution here is correct. I don't know if I could say that properly. Sorry. The solution is correct. Good analysis here. So that's going to be my final answer. Final question for the day. I did 11 problems for today, which is awesome. What I'm going to do is I'm going to stream again at 2 p.m. and I'm going to work on senior level chemistry as well. So some grade 12 problems mostly, and you can tune in for that. So thank you so much for tuning in. What we're going to do is, again, if you want to kind of relook at these problems as well, you can go back and check out the Facebook group at oneclass.com/YouTube. If you want to check me out as well, again, I stream Monday to Friday. Monday, Wednesdays, and Fridays are math, and Tuesdays and Thursdays are chemistry as well. So you can kind of catch me there. If not, stay safe, stay healthy, and thank you so much for watching. Take care.